Okay, so I was going to start with something which dimensional analysis, which is sort of based on Weinberg's power counting, but then we were trying to do a better job of counting factors of 16 pi squares, essentially, which come from loop diagrams. And part of the conclusion of the analysis will be that the scale of chiral symmetry breaking, the expansion of the chiral Lagrangian is not in powers of f pi, but a larger scale, which is about 4 pi times larger. So this was some, okay, so this is like a very old paper. And then more recently, we kind of did this in a more general way. 76, 485. And it gives you some idea of what is meant by having a strongly coupled theory and so on. So just as an example, imagine you were calculating I-pi scattering at one loop. And these are interactions from the order p squared Lagrangian. And we know from Weinberg's power counting that a loop graph, one loop graph from the p squared Lagrangian gives you something of order p to the fourth, and this graph typically will be divergent, so you need to add an extra p to the fourth counter term to absorb the divergences, etc. So if I now look at what this integral is, it's d4p over 2 pi to the fourth. It has two propagators. And it has two order p squared vertices, but if you remember, they came from d mu sigma dagger, d mu sigma trace, f squared over 4. So the 2 pion interaction has a coefficient of 1, that's the kinetic term, but then the 4 pion interaction has 2 powers of f downstairs because sigma is the exponential of 2i pi over f. So every time you have an extra pion, it comes with a 1 over f, which is to say these two vertices are p squared over f squared and p squared over f squared. So if you do this in dim reg, okay, these p's cancel. You get some integral, and these p's are not actually canceling because I'm calling everything p. There's a loop momentum, external momentum, etc. But the net result is that it's order p to the fourth over f to the fourth. And the standard estimate of loops is loops come with approximately a 1 over 16 pi squared factor. And then you're going to get some logs of mu over everything's a p, some external momentum or whatever. So now if you move mu by something of order 1, or take mu dd mu, the mu dependence here is being absorbed into the p to the fourth coefficient. So whatever this p to the fourth coefficient is, it cannot be much smaller than this. Because maybe you were there was some accident and you happened to pick a mu where this coefficient was 0, but if you just change mu by a little bit, generically you're going to get an interaction which is of order pi to the fourth. Let's put it doesn't matter. Pi fourth, p fourth over f fourth, 1 over 16 pi squared. Okay, so that would be the size typically that you would induce for this interaction. Now the order p fourth Lagrangian, these were these Lloyd-Wheeler L coefficients is v mu sigma. I mean, just generically. So we know that, again, sigma is e to the I pi over f. So each of these things brings down a momentum, a pi over f to the fourth power times an L. That's sort of the power counting. And so saying that, so you have something of this size tells you that let's call these the Li, the L1 through L4 or whatever. The Li's are typically of order 1/16 pi squared. That would be the estimate, or at least they should be bigger than or equal to that, because it would be just an accident that they were much smaller than that, because a slightly different choice of mu, changing it from 300 MeV to 400 MeV would induce an L of this size. And you can go look at the fitted values for these coefficients, and they are of order 10 to the minus 3, which is exactly, which is consistent with this kind of estimate. And so if you now look at a generic chiral Lagrangian, so we have f squared over 4, and then you have the leading term, and then I have the next term, which I will, so now this is what I mean by the chiral expansion, d sigma dagger, 4 of them, and then I have, squared, and then to the 4th times some 6 derivatives, etc. The Weinberg power counting says you have an expanding in a power of momentum, and this lambda chi is telling you where's the scale at which the momentum expansion breaks down, because the expansion's an expansion in p over lambda chi. And what this estimate is telling you is that the coefficient, so L is order f squared over lambda chi squared, is order 1/16 pi squared, which tells me that lambda chi is of order 4 pi times the pion decay constant. That is because every loop comes with a 1/16 pi squared. So really this should be an inequality that these coefficients cannot be much smaller than the suppression by the 1/16 pi squared. So this is what we call naive dimensional analysis, and one of the important consequences of that is that the scale of the expansion is not in p over f. If the expansion was in p over f, then for an on-shell pion, p over f is bigger than 1, and you would have no expansion. So there's this extra 4 pi essentially, which is what's making everything work. And in the second paper, because let's put it this way, delta Li because of a shift in mu, or mu dLi d mu, is of order 1/16 pi squared. So Li could be, if Li were 10 times that, that would be fine, because if you shifted it by the, so if you think of mu here, here's Li, and there's some value. As you move mu around, it moves by an amount of order 1/16 pi squared. It's possible that this thing was way up here and Li was much bigger. But if Li was very small and this dot was here, well, that's an accident, because most of the curve is of order 1/16 pi squared away. So this is, so this is not a rigorous argument in that sense, okay? It's just an estimate of what's going on, but it's still very helpful because it tells you how to estimate sizes of terms which you haven't included. Okay, okay, so then what we did was, for a general EFT like SMEFT, we showed that where you now have an expansion in inverse powers of, we call it lambda there. The Lagrangian has the following structure. Derivatives over lambda to the A, 4 pi times scalar, basically every field comes with a 4 pi. 4 pi times fermion fields over lambda to the 3/2 to the C. Same, gauge fields behave like bosons. And then if you have coupling constants, you get G over 4 pi to the E, Yukawa over 4 pi to the F, lambda 5/4 couplings over 16 pi squared to the G. So this just tells you, if you have some operator with some number of fields and some number of couplings, this is an estimate. If you assume that the terms are of this size, that's sort of the size they would be in a strongly coupled theory. So for example, if you take so you take 2 phi's, then you have lambda to the 4th over 16 pi squared. and two derivatives, so d over lambda squared, 4 pi phi over lambda squared. And you can see that you're getting something of order d squared phi squared, which is exactly what you would expect for the size of the kinetic energy term. And then you can keep going. And this is consistent in the following sense, that if I take loop graphs, arbitrary loop graphs, where every vertex obeys this power counting, then the new interaction I generate in this sense that I'm varying some log to, I'm just doing this loop estimate, gives me something which is consistent with this formula. You cannot have coefficients which mess this up too much, because if your coefficients were too small, then the loop graph would induce coefficients of this size, and so this is like a consistent power counting for a generic theory. So in other words, what you should do, and we did this for SMAFT, is you write the Lagrangian as some operator like this times some C hat, and you expect by the power counting that all your coefficient C hats are sort of order 1 where the dimensions are counted this way. But the reason for this is important is that if you go look at the SMAFT operators, for example, between h to the 6, h dagger h cubed, and look at the different operators, so you can look at some papers we did. There's a difference of factors of 4 pi here between, I should have written it down, but it's like between the maximum term and the smallest term, there's like some difference of like 4 pi cubed or something, which is 6 orders of magnitude in how you should scale the coefficients. So it makes a big difference in when you're estimating terms. So what it's telling you in some sense is if the theory is perturbative and g and y and lambda are much smaller than 4 pi, then you get an additional suppression, which is the usual perturbative suppression like this. So for example, a one loop diagram will have g squared over 16 pi squared. So this is the alpha over 4 pi coming from loops. But you can make the couplings big. And a strongly coupled theory, this would be sort of order 1. But you cannot make it bigger than 1 because you would completely mess up the whole power counting. Because the loop corrections can be smaller than the terms you have, but they can't be bigger than the terms you have. Because if they're bigger than the terms you have, then your assumption of how big the terms were was wrong. And so this also tells you that if you take these perturbative couplings, the best you can do, or the strong coupling theory, is when gauge couplings are order 4 pi, Yukawa couplings are order 4 pi, but then the lambda 5/4 coupling is order 16 pi squared. And that's because these two couplings involve 3 fields, and this one involves 4 fields. So it sort of also gives you the estimate of what, people have used as what is strong coupling, when the one loop diagram is comparable to tree level, basically, is what's happening. And if you take this for, okay, so now we have too many pi's, because some pi's are pi's and some pi's are pions. But if you take this and apply it, let's just call it phi for now. And I take this relation, where is it gone? Lambda is 4 with an equal sign, then this becomes phi over f, which tells you that you can have phi over f, the scalar field over f, to arbitrary powers. And that's consistent with the sigma being e to the 2i pi over f. All the terms in the exponent are order 1 in the power counting, and this whole sigma is the same size in power counting. It would be weird if the different pieces of sigma had different power counting. And this lambda chi, which is about 1 GeV, also is, the row mass is also of the same size and so on. So anyway, so the typical, if you want to estimate the size of corrections, chiral corrections, you suppress the higher dimension operators by powers of lambda chi, and then use lambda chi about 1 GeV, and that will give you a good estimate of how big the corrections are. Well, or you can NC, and yeah, you could do more sophisticated things. Yeah, let me, there's some, okay, let's not do large NQCD for now, but let's just stick with what we have. Okay, So the next thing I wanted to do was symmetry breaking. Okay, now you'll see we can get to some interesting stuff. So we started with massless quarks. The chiral symmetry was exact. The pions were exact Goldstone bosons and were massless. And now I'm going to add to the Lagrangian the mass term, which is minus q bar left m q right minus q bar right m dagger q left, where the mass matrix is mu, md, ms. Now this explicitly breaks the chiral symmetry, because if I made a transformation here, the q left would have an L dagger, the q right would have an R, and the L dagger and R don't cancel. So you've broken the symmetry. So the standard way to handle symmetry breaking like this is what's called a spurion analysis, where you pretend that M is like a background field. It could even depend on X. You have some, and you assume M transforms like LMR dagger. That's why I wrote the other thing as M dagger. If you do that, then this Lagrangian is chirally invariant. And what you do is, the symmetry is broken because after you finish your calculation, you plug in M equals a specific value, and that's breaking the symmetry. It's like if you have some atom in a magnetic field, if you treat the magnetic field as a vector, then you haven't broken rotational invariance, because everything will rotate along with the magnetic field. But then when you set the magnetic field as pointing in the z direction, now that breaks the symmetry because you've picked the z-axis as a preferred axis. So in that sense, okay, so this is a standard thing for studying symmetry breaking. People do this all the time. If you are doing axion physics, for example, where you have this, I'll just mention it, the axion term in terms of GG dual, by making a chiral rotation, you can actually put the axion field into phases of the mass matrix. And so this analysis I'm doing for pions is also what's used to calculate masses of ALPS and so on. And it's related to the pion mass. Okay, so in the EFT, what do we have? Well, we're writing down the most general possible Lagrangian consistent with chiral invariance. And now we have one new object, which is M. And I want to do perturbation theory, so I want to write down the terms which I can have, which have 1 power of M and the smallest number of derivatives. That would be the leading perturbation. And there's a unique term, which is usually written as f squared over 2b times the trace of M sigma dagger plus the Hermitian conjugate. So now you can have a term with no derivatives, because the M here has an LR dagger transformation, and then these terms are chirally invariant. Previously, we had to have sigma sigma dagger, which was a constant, but now with M there, this is no longer a constant. Okay, so the mass term is order 1. It has units of mass dimension 1. This is something with mass dimension 3, and it's written this way for historical reasons. So B has mass dimension 1. We don't know what it is. And so that's the leading order correction, the leading order in M, the first order in M correction in the chiral Lagrangian. Is this clear? Well, we'll come to that in a second, yeah. Okay. So then you can work out what this does. Again, expand sigma in powers of the pion. And the 2 pion term is minus 2b trace of M pi squared plus dot dot dot. So the f squared was put here because when you expand with 2 powers of pions, you get 2 factors of f downstairs, which kills the f squared, which is why this is minus 2b. And I wrote down yesterday what that pion matrix looked like. M is mu, md, ms, diagonal. That pion matrix I wrote down, multiply them together and take the trace. And you can read off, so you'll get terms which are like minus a half something pi 0 squared, etc. And then whatever is in front of the pi 0 squared, that's the mass of the pi 0, or m squared of the pi 0. And you'll get terms which are eta squared, pi plus, pi minus, etc. So you just do the trace and you can read off what everything is. And you find that m squared pi plus or pi minus is b mu plus md, m squared pi 0 is b mu, well, okay, let me not do the pi 0 yet. K plus k minus is b mu plus ms, m squared k0 bar is b md plus ms. And then in the pi 0 eta sector, you get a 2 by 2 mass matrix. So in the pi 0 eta sector, you get a mass matrix, which is B times mu plus md. Here you get mu minus md over square root of 3, mu minus md over square root of 3. This is mu plus md plus 4ms. Okay, so completely straightforward calculation, just do the trace. Now I'm going to do one thing here, which maybe if I have time I'll discuss. If you include electromagnetic corrections, then you get a correction to the charge mesons because of electromagnetic effects. So I'm just going to call that delta E and M. And there's a result due to Dashan, which says that the correction due to electromagnetism in the pion and the kaon are the same. You can see, write this in terms of a chiral perturbation theory operator, which I don't know if I'll have time to do. So just take this for right now as given. And so these give me the masses of the mesons. Now you have to diagonalize this pi 0 eta mass matrix. So you can see that, okay, so let's work in perturbation theory. So m squared pi 0. So I'm going to treat the off-diagonal term as a perturbation. So this is quantum mechanics if you want, or eigenvalues of a 2 by 2 matrix. So the first term is b mu plus md, and m squared eta is b mu plus md plus 4ms over 3. And then the next correction, okay, if you have an eigenvalue problem for a 2 by 2 matrix like this, the next correction is the off-diagonal element squared divided by the difference of these two diagonal elements. And so the corrections here are order mu minus md squared. And if this one, the lighter one goes down and the heavier one goes up by the same amount, this is just the standard. If you're doing quantum mechanics perturbation theory, the shift in the energy level, delta E goes like, E0 is like 0hn squared over E0 minus En. Summed on n. So here's E0. This is the off-diagonal element. There's only two states. So this is n equals 1 is this element, and then the denominator is E0, which is this term, minus E1, which is that term. The lowest order in perturbation theory results are just E0 is this element, E1 is that element. So the standard quantum mechanics perturbation theory formula is just the same as expanding eigenvalues of a matrix in perturbation theory. So okay, so mu minus md is isospin breaking because isospin rotates the u quark into the d quark. But what's interesting here is that the pion and the eta mass shifts from these terms are actually, this is second order in isospin breaking. And so that's quite small because isospin breaking, if you want experimentally, is of order a few percent. And so the second order effects are negligible at this level. The electromagnetic corrections are comparable to isospin breaking. I mean, this is things you have to take essentially phenomenologically because it has to do with the relative size of alpha electromagnetic relative to the up and down quark masses. It's this over ms. Yeah. Yep. That's right. So if you look up the, well, it's sort of backwards, but if you look at the PDG quark mass values, this difference is about 2, 3 MeV, and that's 70 or 80 MeV, and so you get a very small shift. This is backwards because it's the meson masses and things which are used to, in fact, extract the quark masses, but okay. Okay, so first of all, we find that the mass squared of the Goldstone bosons, so first of all, they're not Goldstone bosons anymore, they have a mass. They're approximate Goldstone bosons are what's called pseudo-Goldstone bosons. But the mass squared of them is proportional to the quark mass. So it's the mass squared of the meson, which is linear in the quark mass. Or the meson mass, if you want, goes like the square root of m quark. So these are these non-analytic terms that occur in the chiral expansion. 2, we do not know the cannot determine the overall scale. So experimentally, we know these meson masses, but everything has a b in front. So we can only determine b times the quark mass. So we don't know the absolute value of the quark masses from chiral perturbation theory. But we can get mass ratios. And so Weinberg did this. So I'll leave this as an exercise, but just, okay, if you take suitable linear combinations, you can get mu over md, which is m squared k plus minus m squared k0 plus 2 m squared pi 0 minus m squared pi plus over m squared k0 minus m squared k plus m squared pi plus. Okay. So I just verify this. Just plug in these formulae for all the m squareds, and you'll see that you end up with the ratio mu over md, and this delta electromagnetic cancels, etc. And ms over md is m squared k0 minus m squared plus m squared k plus minus m squared pi plus over m squared k0 minus, yeah, the d is the same as the above, plus m squared pi plus. So we can determine the quark mass ratios, mu over md and ms over md, where the b drops out. And so plugging in the known values of the meson masses, you get 0.55. And here you get 20.1, I think. Okay, so already we have some interesting information from chiral perturbation theory that, well, the S quark is significantly heavier than the down quark, but also U and D are not that close together. The U quark is about half the mass of the D quark. And in addition, you get one more relation, which is called the Gelman-Okubo formula, which says that for m squared k0 is 3 m squared eta plus m squared by 0. So independent of all of these quark masses, this relation has to be true. And experimentally, this side is 0.99 GeV squared. And on this side, you have 0.92 GeV squared. So it works pretty well, given that we're working to first order in perturbation theory, and there'll be second order corrections proportional to ms squared and so on. So already we have some useful information on the quark masses and the structure of the meson masses as well. So the statement that ms is much heavier than md means that the kaons and etas are much heavier than the pion, etc. Okay, now we can do something interesting in the QCD Lagrangian. So when you're doing a path integral, the the action here, e to the I action, is the QCD Lagrangian, which is the kinetic term minus the mass terms. Now, if I differentiate this path integral with respect to the quark mass matrix, so let's say I differentiate with respect to Mij, and I'll treat M and M dagger as independent objects, or you'd have to write M as a real and imaginary part and differentiate to real and imaginary. But the thing about the functional integral, the fact that the field theory is a functional integral, means that when I differentiate this, I pull down the operator Q bar Q. So d by dm on the path integral gives me the matrix element in the vacuum of minus Q bar left I, Q right J. And the minus sign just because there's a minus sign there. And so if I do d by dm at m equals 0, I'm getting this condensate in the massless theory. Now I have an EFT, and I can do the same calculation in the EFT. And the EFT is reproducing the mass dependence, all the low energy dynamics of the M. So the EFT calculation gives me f squared over 2 b. And then if I differentiate the M here, I just pick out sigma dagger Ji. So I get the expectation value of sigma dagger Ji in the massless theory. So by differentiating the QCD and the EFT with respect to sources, I can get some information on what's happening here. And when I expand out sigma dagger, okay, so sigma dagger Ji is delta Ji, and then there are terms which are pion, 2 pions, etc. But the matrix element in the ground state of the pion is 0, and then the 2 pion matrix element would be a Feynman diagram like this. But if the pion's massless, this thing gives you a scaleless integral, and it's 0, etc. So this just becomes f squared over 2b, I'm sorry, f squared over 2b delta Ji. Okay, is this clear? I'm just comparing expansions in QCD versus the EFT. And so if I now take f pi squared m pi squared, f squared m pi 0 squared, so that's b f squared mu plus md. So bf squared, so this is minus 2 q bar left, q right, mu plus md. Now, the way this is usually written is if you take q bar q, that's q bar left, q right, plus q bar right, q left. But because parity is a good symmetry, the matrix, the expectation value of q bar left, q right is equal to that of q bar right, q left. So twice q bar left, q right is the same thing. So you get, this is the same thing as the minus the expectation value of q bar q, mu plus md. So this is a famous relation by Gell-Mann, Oakes, and Renner, which says that f pi squared m pi squared is the quark mass times the value of the condensate. And again, if you do axion physics, you will find that f axion squared m axion squared is something which is proportional to this, or really you get some relation which says that f axion squared m axion squared is equal to f pi squared m pi squared times some constant of order 1 connected with exactly how the axion couples and quark masses and so on. Well, because in the ground state there's no pion. You're starting at 1, that's the vacuum. Well, then you have to find the minimum of the chiral potential and expand about that point, but which is what's done. Okay, that's a good question. So that has to do with the sign of B, and I kind of said that B was positive, and if B was negative, so what are we doing? We have some manifold, this is the origin. Previously, the entire surface of the sphere was constant energy. Now when you add the mass term, we're finding that there's a minimum here, and you do some small perturbation, and you get quadratic shifts in the energy, and those are the masses which we read off. Now if B were negative, this would be a maximum instead of a minimum. And the ground state would go somewhere else, like to the South Pole or something. And actually, Dashan worked out some of this stuff and found that he was trying to look at whether CP could be spontaneously broken in the chiral Lagrangian. So if you want, at this point, we would take this as an ansatz that it's, well, experiments telling you kind of it was positive. And this is related to whether the theta parameter could be pi or not. And you can flip a sign. Because if you flip all the signs of the quark masses, that's like flipping the sign of B and so on. So people have looked at it, but so we'll just assume right now it's positive. So if it is it doesn't have to be positive, it just means that we expanded sigma about pi equals 0, and that wouldn't be correct. You'd have to minimize the potential and expand about the correct minimum. The condensate has to be negative, that's right. Okay, so all of this stuff, okay, so we know the condensate times the quark mass, or effectively we know B times the quark mass, but we have neither of them separately. So there's various methods people have used to extract the quark mass itself. I mean, nowadays the direct method would just be the lattice, where you compute on the lattice, convert to the MS bar scheme by some renormalization, and the thing M bar, which is the average of the up and down quark masses, is easier to simulate on the lattice because you don't have to put in isospin breaking. And the PDG value for this is 3.45 plus 0.35 minus 0.15 MeV. This is the MS bar mass at mu equals 2 GeV. So if you now put this in and take F pi squared M pi squared and divide by the MS bar quark mass, you get the condensate renormalized at the same scale. And so you find that minus Q bar Q at mu equals 2 GeV is numerically about 280 MeV cubed. And there's this whole technology of QCD sum rules with condensates and so on, where they try and extract these and the gluon condensate and so on. But, okay, so here's one example of something we can do. Now, there's one other thing I should mention about the quark masses, which was kind of fun when we first did this, I don't know, sometime in the 1980s. It's not so relevant now, but still it's worth keeping in mind. So the quark mass matrix transforms like L, M, R dagger. And so the determinant of the quark mass matrix transforms to the determinant of the quark mass matrix, because L and R are SUN matrices with determinant 1. Now M dagger transforms like R, M, L dagger, taking the dagger of that, and M dagger inverse, taking the inverse of this, transforms back like L, M, R dagger. Now, M dagger inverse is not a good thing to use for perturbation theory because it's going like 1 over the quark masses. But if I multiply it by determinant of M, this is second order in the quark masses because dead M is cubic. It's a 3 by 3 matrix. And this transforms exactly like L that M dagger inverse R dagger. It transforms exactly the same way as M. Now in chiral perturbation theory, all that matters is how everything transforms under the chiral symmetry. That's the only input we're taking. So if somebody gave you a chiral Lagrangian, you could always make the replacement M goes to M plus lambda at M dagger inverse, and you can't distinguish the two. So this is work was done with David Kaplan. So this is like some invariance of the chiral Lagrangian under a redefinition of the quark masses. Now if you look at the case where this mass matrix is mu, md, ms, then the determinant of M is mu times md times ms, and the inverse is just 1 over these. So in other words, this is md ms, mu ms, and mu md. So if you make this replacement everywhere, there's no chiral extraction of quark masses which can tell. So one person's mu, md, ms can turn into another person's linear combination like this. And the reason we were interested in this is suppose the up quark were massless, then you solve the strong CP problem because there's a quark, you can make a chiral rotation to remove theta. And you might think that that's in conflict with chiral perturbation theory and all the extractions of the meson masses. But if you set mu to 0, this becomes 0 mdms, and then you get lambda here, mdms, 0, 0, and you have an effective up quark mass. And so we argued at that time that, well, when you had a lambda which was consistent with the power counting, maybe twice as big or something, you could explain the chiral perturbation theory would work, and you could have an up quark mass which was 0, and the strong CP problem would be solved. Now, on the lattice, unfortunately, you can tell these two apart because you can vary the quark mass in the QCD Lagrangian, and you can determine what's linear and what's quadratic. And it turns out, at least as far, they seem to, at 5 sigma or some high level, rule out the lambda you would need for this solution to work. So we're still stuck with the strong CP problem. Because this is the M of the QCD Lagrangian. So what matters is what was in the QCD theory. And what's happening is a second order term like trace. So we wrote it down in the paper, but like trace sigma dagger M, sigma dagger M. Some linear combination of terms like this can mimic the term over there. Again, it's related to the Cayley-Hamilton type identity because this thing only is valid for 3x3 matrices. So any questions on this? This is just saying that your theory has two things which transform the same way, you can't tell them apart. Not in the chiral theory, but from the lattice, yes, because you can look at what's linear and what's quadratic, and then you can determine what the analog of lambda is. So this corresponds to some redefinition of the Gasser-Leutwiler coefficients, and then if you can determine them from some other method, which they do on the lattice, then this ambiguity isn't there. Okay, so the next application I wanted to do was pi-pi scattering. So we've had some lectures on this. Hopefully the formulae agree with the previous lectures. So we had there's some whole arguments about this, but it doesn't matter because we have NC is 3, and you can look at how big 1 over n corrections are. So that was like a fake objection. I mean, I think the real thing is you can now check what is quadratic and what is linear, and it's ruled out as far as I can tell. Okay, so we wrote down the kinetic energy term, traced d mu sigma dagger, and the 2 pion piece of that was simply the pion kinetic energy term. And if I expand to 4 pions, I think I may have written this down already, you get 1 over 3f squared, the trace of pi commutator d mu pi whole squared. And then you get 6 pion terms, etc. And here, we expanded this out to quadratic order, and that was the pion mass term. And you can also expand this out to 4th order, and you get plus 2 over 3f squared b trace m pi to the 4th. And again, there are 6 pion and high order terms. Okay, so just doing the series expansion to order 4 pions in this term and the kinetic energy term. And if I do this for SU2, just to avoid complications, then the commutator of two of these factors gives you the commutator of 2 generators, which is epsilon ABC, and then epsilon times epsilon can be written as deltas. And so for SU2, this is is 1 over 6f squared pi dot d pi squared minus pi dot pi d pi dot d pi plus 2 over 3 f squared, sorry, plus m pi squared over 24f squared pi dot pi squared. Because b times the quark mass is, we can use the fact that that's m squared pi, well, m squared pi 0 is b mu plus md. And so that gives you this. Let's just work in the isospin limit where mu is equal to md, but I think it doesn't matter. So this is what you get. Okay. So this is the leading 4 pion interaction. There's no free parameters. Because we know f from pi decay and we know m pi, so that's what you have. Okay, so here's an exercise. So calculate, so use Anand's notation, A, B, C, D are the isospin labels of the pions, and then the momenta are PA, PB, PC, PD coming in. And S is PA plus PB squared. T is PA plus PC squared. U is PA plus A plus D squared. You just take this matrix element. Okay, so it's a good exercise to just take this operator. You have the different ways of contracting things. And the amplitude you get is I over F squared delta AB delta CD S minus m pi squared plus I over F squared, and then it's completely crossing symmetric delta AC delta BD T minus m pi squared. So let's put it down here, plus I over F squared delta AD delta BC U minus m pi squared. And of course, ST and U are not independent. S plus T plus U is 4 m pi squared. But this way, it makes the symmetry manifest, I mean, the Bose symmetry. Okay, so this is the pi scattering amplitude, and I think it's hard to read what he's writing from that corner, but I think this is what he had. Okay, so no parameters, we have the full pi. So this is the leading chiral amplitude at order p squared. Oh, and so you can see from here that because physical particles have p squared equals m pi squared, which is proportional to the quark mass, So in answer to your question, the power counting which is applied in chiral perturbation theory is to say that the quark mass matrix counts as order p squared as far as power counting. So when people write down the chiral Lagrangian to p to the fourth, it has either 4 derivatives, 2 derivatives and 1 m, or 2 m's. And that's what's used. And so you can see here, okay, these s and so on are second order in momentum and the pion squared. So that's consistent with this. So m pi would count as order p. If you, well, it's I mean, because it's coming with a b in front and stuff, right? So what people do is well, if you apply this naive dimensional analysis power counting, you will find that b should be of order, yeah, it should be of order lambda, basically. Yeah, it's consistent with what he says, yeah, that's right. So it's bm, I guess maybe the better way to say it is it's bm over lambda squared, yeah. Because yeah, that's right. Okay, so now we can work out the scattering amplitudes in the different isospin channels. So we have pi a pa plus pi b of momentum pb coming in. This is an isospin 1 particle, that's an isospin 1 particle, so you get isospin 2 plus 1 plus 0. Now what is the linear combination of pions, which is isospin 0? That's where, if you think of this as some kind of initial wave function, it's a superposition of these proportional to delta AB. That is pi 1 plus pi 2 plus pi 3, that's the isospin 0 channel. Or if you think of, yeah, let's just leave it that way. So if I multiply this by delta AB, then I will end up with is something proportional to delta CD, that is the final state is also isospin 0. And the amplitude in the isospin 0 channel is I over f squared. And here, this term, when I multiply by delta AB, gives me a 3, because delta AB is 3. So you get 3s minus 3m pi squared. This term, when I multiply it by a delta AB, gives me delta CD with a coefficient of 1. So that gives me plus t minus m pi squared. And the last term gives me plus u minus m pi squared. So this whole thing is I over f squared 3s plus t plus u minus 5m pi squared. Okay, if I wanted to look at the isospin 1 channel, the way you combine two isospin 1s into something which is isospin 1 is something which is anti-symmetric in this. That is basically an epsilon, let's say GAB or something. So if I take this thing and I multiply it by something which is anti-symmetric in AB, the first term goes away because delta AB is symmetric in AB. And here, if I multiply it by something anti-symmetric in AB, the second term, the third term is swapped, the A and B. And so when you anti-symmetrize, you get a minus sign. So the isospin 1 channel amplitude is t minus u, because you get t minus m pi squared minus u minus m pi squared. And the isospin 2 amplitude is multiplying by something, some tensor TAB, which is symmetric and traceless. That's how you combine two isospin 1s into isospin 2. So if it's traceless, the delta AB doesn't contribute again because it gives you the trace. But now these two pieces have the same sign. And so the isospin, let's put it here, the isospin 2 amplitude is I over f squared t plus u minus 2m pi squared. So these are the pi scattering amplitudes in the in the different channels. Okay, hopefully these agree with what is written down. Now at threshold, S is 4m squared, and T is equal to U is equal to 0. And so the isospin 0 amplitude is I over f squared. Okay, so that's 12 minus 5, and these two are 0. So you get 7m pi squared. The isospin 1 amplitude is 0. And the isospin 2 amplitude is I over f squared minus 2m pi squared. So these are the threshold scattering amplitudes. There's a length which people have defined in chiral perturbation theory, which is m pi over f pi squared. So this turns into, so let me do 2 steps. And there's something called the scattering length. A, which is minus I times the amplitude over 32 pi m pi. Okay, so forget why. This is some historical thing, and I don't have no idea why it's done this way. But if you plug this in, you find the pion scattering length in the isospin 0 channel is 7/4 times L. In the isospin 1 channel is 0. In the isospin 2 channel is minus a half L. Okay, so these are the famous formulae that Weinberg derived for the pion scattering lengths in, I think, 1966, when nobody knew what QCD was or what a pion really was or anything. Just some strongly interacting particle. And it's governed by this m pi over f thing. This should agree with what Anand did. Okay, so this is with chiral perturbation theory. We have it's some non-trivial, this is like some Clebsch-Gordon coefficients or whatever, but here are this is the pi scattering at threshold, and actually we can even go away from threshold. So this formula is for the scattering amplitude away from threshold, and as long as all of these things are small compared to lambda chi, so the corrections to this are like order s squared over lambda chi squared. By s squared, I just mean s squared, st, t squared, etc., quadratics in all the variables. Okay, so I think time's up anyway, and so anyway, I gave you some applications now. We were discussing the theory, but we have some applications, and you could go do 6 pions or something if you wanted pi to 4 pi. By just taking the chiral Lagrangian and expanding to order pi to the 6, and you have again, no free parameters, you can go calculate that amplitude, the scattering amplitude for that. Okay, so questions? I didn't put any homework really, but all the homework is essentially just, take the sigma, expand it out, and verify all of these results. And what? Fill in the gaps, yeah. And it's not, have a Mathematica file with the pion matrix defined once, and so you don't have to keep typing it in, and then you can just do the traces. It's pretty straightforward. Okay, any